Just something really neat that I've never actually done, but since we've got the interfaces working, I'm gonna try to do it live this week, okay? Actually, we probably can, because I think it's supposed to be cloud in right on Friday. I could be wrong about that. We need a sunny day so we can put up a lot of charge, so, okay? Now, if we charge this thing up, you know, we crank the generator or the whip search machine and charge this up to where we're getting sparks that long. That means we've got tens of thousands of newtons per coulomb, okay? Yeah. Pretty substantial electric field. And then all of a sudden we get a spark and it discharges, okay? Or somehow we discharge. And there are various things that we can do and various ways we can do that. Well, we don't actually have a current, like especially when this thing's charging up, we're not getting a current across here. But we're getting a lot of electric flux. So let's say in 10 seconds, this thing has an area of ballpark 0.03 square meters, right? Okay. Then what's the electric flux in between these? If we build up from, let's say, no charge to 50,000 newtons per coulomb in 5 seconds, just make the arithmetic easy, okay? So what would our flux as a function of time be? Okay, so I'll remember all the details. Okay, so we've got 2 plates. Build from 0 to 50,000 newtons per coulomb in 5 seconds. What is your electric field flux? Imaginary surface between plates. Okay, well, do this real quickly. I think I saw one good solution out there. We could do electric field with time. It's going to go from 0 50,000 newtons per coulomb in 5 seconds. Meaning it's a straight line from here to here, with a slope of 10,000 newtons per coulomb per second. Okay. I'll say 10,000 newtons per coulomb second times speed. Okay. So what's the flux? Well, flux is just the electric field times the area. So that. Well, it's gonna be 0.03 meters squared times this, which is gonna be 300 times 10, 0.03 times 10,000, 300. It's gonna be meters squared per coulomb second. Whatever in the world that means, but it's the units you need for things to work out. And if I've done that right, then I can have a certain amount of faith that when I now calculate the rate of change of this flux, I'm gonna get something that makes sense, okay? So, here's what we got. Okay. So. Good is easy, right? Now we could have a more complicated question. We could think this probably goes like this. So you get a much more rapid increase down here at the beginning than you do at the end. Okay. Then, of course, when the spark flies, it all goes to zero very, very quickly, right? Okay, so this should produce a magnetic field. This change in magnetic flux should produce a magnetic field. Okay. And that magnetic field should be equal to four pi k prime or mu naught. Again, k prime is 10 to the negative seventh. Get that. And epsilon naught, which is 1 over 4 pi k, right? Times d phi e z p. Okay. Remember, k is like 9 times 10 to the 9th. And let's go ahead and suppress the units. Act for a moment like engineers. Just say, units going to work out. And then think through the units. Okay. And we've got units on this. Got units for k. Okay. 50 meters squared per coulomb squared units of k prime. That's what we got. Meter. Yeah. I think I did that right. I got to write it out and work it out. Okay. The 4 pi's, of course, go away, so just get k prime over k. Well, that's going to be a pretty small number, right? K prime is like 10 to the negative 7th. And k is like 10 to the 10th. You're going to get like 10 to the negative 17th. Not a very big magnetic field. Okay. So I wanted to work that out to see if there's a possibility we could measure it, detect it somehow. Not at that way. Okay, even though we could get a much quicker increase when we start cranking the generator. Still not gonna do it. When the thing discharges, then the time interval is going to be a whole lot less than 5 seconds, right? And it's going to fall from, say, 50,000 newtons per coulomb to 0 in less than a millisecond, maybe a microsecond. Okay. And if that happens, microsecond is 10 to the negative 6 seconds, so we get a factor of maybe 10 to the 7th. That would give us on the order of 10 to the negative 10th test. I don't think we can detect that with our instrumentation. Okay. So I think it's safe to do this without messing up all the compasses in the columns. Okay, but I don't think we're going to be able to measure this. I think it's a thing to think about. Well, that illustrates what we call displacement curve. Okay. And there's a little bit more to it. I wasn't thinking clearly when I said that should be equal to the magnetic field. The magnetic field is such that the integral of B dot ds around the perimeter ought to be equal to this. Okay. So it's going to have units of magnetic field times distance, not just magnetic field. Now, the distance around this thing is on the order of a meter. So the numbers that we estimated are still going to be valid. If you divide that integral by that distance, you're still going to get something in the order of take a negative 10. Tesla. Now, the magnetic field of the Earth is on the order between 10 to the negative 5th, 10 to the negative 4th Tesla. Okay, so there's still like on the order of 100,000th to millionth of the magnetic field of the Earth, which is why you're not going to deflect the compass, and even our instrumentation, which is somewhat more sensitive than compass, is still not going to detect it. Okay. Still changing electric fields, as you can kind of see from this example, if you believe it. And be nice if you could detect it so you really believe it and take our word for it. Changing electric flux gives rise to magnetic field, and that's why light travels through vacuum. Okay, you got a magnetic field and an electric field. Magnetic field changes, inducing an electric field, and the electric field changes, induces a magnetic field. That's like they go as signs. Okay, and they travel in direction perpendicular to the electromagnetic fields. Now you understand it, right? So when you go out in the sunlight, you can calculate what's happening. Coming through a vacuum from medium to medium. These laws take care of it. There's more we could say, but I want to sort of concentrate on LRC circuits. Something we don't, there's a chapter there we don't have time. We just can't get there. But since you have the differential equations background, kind of short some of that. I do want to talk about that circuit and that equation. Okay. Now, they're parallel in series LRC circuits. We're going to kind of concentrate on series LRC circuits just as time constraints. We might be able to talk about the others, and we might be able to detect some of this in lab. although I don't have a good function generator. Okay. Got one, it's not good. But, see this picture in your book, you got a capacitor and an inductor and a resistor. Switch. In parallel with that, you got an AC source. Or some kind of a source. Actually, it's like this. Direct current source. And you've got another switch. Okay. You can keep this switch open and close this one. Now you don't want to close both of them. Because if you close both of these switches, you short circuit source. Now with the battery, it's got some internal resistance and nothing too bad happens. You got a more powerful source with very low resistance, you just kind of blow up. Okay, so you got to be careful throwing the switches. So let's say we're using a battery. And well, you close this switch and what happens? You try to drive a current through this thing, but it resists it. Lenz's law. You're trying to increase the current in this, but that causes an increasing magnetic field, which produces an opposing EMF. Okay. So this thing, yeah, if there's no capacitor, just this and a resistor, as we saw last time, sort of, we have an exponential approach to just voltage divided by this resistor, right? Yeah, no capacitor in here, that's okay, we can do that. All right. If the capacitor is not there, then what we can do is we can simultaneously close this switch and open this one. And now we've got a current flowing in here, and it can't drop off to zero instantly because the current drops. That changes the magnetic field inside this core, a solenoid or whatever it is. Solenoid's the easiest thing to use because you can easily calculate the magnetic field that's inductance. We'll do that. But so the field's going to exponentially decrease to zero. Now you can detect exponential increasing and decreasing voltages and or currents with capacitors. Okay. Did last week. So yeah, that's at least intuitively believable. And we've kind of analyzed those exponential curves, which sure we have the mathematics of those. Okay. Now, the really cool thing is if you've also got a capacitor. Okay. Now the capacitor also, it tends to slow down the increase in the charge in the current. Okay. Because you're pushing charge onto here, pulling it off here, and getting an EMF that lights source. And we talked about that a number of times. So we have that whole idea. Okay, so at some point, you're going to have that capacitor all the way charged up. Okay. Well, you don't really have to open these switches simultaneously. You could, this one's already open. You could just open this one. Then what would you have? You'd have a charged up capacitor and no current. You know, assuming you leave the switch closed for a while. Okay, essentially no current. Theoretically, you're pushing it as an asymptote, but that last electron gets transferred and it's done. Okay, and that will actually happen depending on the capacitance and the inductance and the resistance and so forth. It won't take all that long. Okay, so get to the point where there's zero probability, well, less than a 50-50 chance that an electron is going to get transferred one way or the other. Actually, not quite that simple, but okay. And if it gets much more complicated, I can't have it. Yeah, for quantum mechanics. So, I've got the mathematics to do it. That just be following the formulas. Okay. That aside. So now we have the capacitor charge low. No current flowing because these switches are both open. So we close this switch. So what do you think's going to happen? Okay, so the capacitor is going to discharge. Okay, again, you got the capacitor charged up. You open this switch, then you close this switch. Capacitor's charged up, it's going to discharge. That's obvious. You know, you have your hands on the capacitor, you know how they act. And some idea how they might act in an alternating circuit. That's kind of what we're doing with a hand simulated square wave. Okay. Yeah, it's going to tend to discharge. It's going to discharge instantly. Well, you know, you've never seen a capacitor discharge instantly because there's a resistance there, right? Of course, when you said they don't charge, it doesn't discharge instantly. You said it was because of the inductance. Well, it's actually because of both. Okay. As it discharges, even if the resistor wasn't there, it couldn't discharge instantly because of the inductance. And that's really what we want to focus on. Okay, we'll take the resistance out. What's going to happen? Well, you're going to discharge the capacitor, not instantly because the inductor prevents you from doing it instantly, right? But at some point, the capacitor will be totally discharged. Okay. There's still going to be a current flowing in the inductor. And the current flowing in the inductor doesn't want to go to zero. So what's going to happen? The inductor starts pushing back and charges the capacitor up. Capacitor gets totally charged. Now there's no current. Capacitor discharges through the inductor, which builds up a current. Capacitor is totally discharged. Inductor current's at its maximum. And it pushes back, and so you get this oscillating current. And that's how you get oscillating currents electronically, okay? A second. Now, there is a little bit of resistance in any circuit. There's resistance in the wires of the inductor. But if you build the inductor some other way, then you can do that. I don't know how to do it. So eventually the current's going to dissipate. But you're going to have a sine wave current with a decreasing amplitude. Okay. And you'll have that also if you got a resistor here, depending on how big the resistance is. If the resistance is too big, it'll just lock to zero. Well, you've seen solutions of second order differential equations. I don't know if you dealt with the approach to resonance, which is always one of my favorite things. And I know you did a lot of things that I don't do too, of course. But, you know, different people teach a different course, it's not standard course. And I think mine are pretty good too. Okay. I kind of, maybe one of the reasons I concentrate on approach to resonance is it took me a while to figure that one out when I took undergraduate course. Okay. And I had a puzzle on that for a while, and the trigonometry, it's just manipulative trigonometry. It's fairly complicated and somewhat hard to understand. And it's really understandable. It's worth looking at the approach to resonance. Did you do any of that? Yeah, you did something. That's good. I think it's important. Because again, an electrical, mechanical engineer, they're kind of have to deal with resonance in positive and negative ways. Or sometimes you don't want it like we do. That's what a civil engineer does, not a mechanical engineer. You build some kind of device and you don't want it resonating because it'll blow apart. Okay. But in electrical, a lot of you want that kind of resonance because that's how you amplify your signals. Okay. Okay, so anyhow, these LRC circuits are really, really a big deal. Also, it's analogous with mechanical circuit. Oscillation. And you got mechanical resonance. Take that pendulum, if I keep pushing it with the right frequency, it's going to resonate. Okay, if I push it with the wrong frequency, it's just going to kind of not behave very well. It's not going to ever build up a sustained oscillation. So as we get the resonance, the more the semi-chaotic motion, you're going to get more semi-chaotic motion. Okay, but unless you're in a resonant frequency or multiple of the resonant frequency, not going to work. Okay, you solve the equations, the differential equations for mechanics. The spring matches that. Okay. You got a spring. If there's a mass in the spring, if it's just a mass in the spring, then it's going to have a natural frequency. So just a mass in the spring is analogous to this. No resistance. Okay. An ideal spring. And there's a natural frequency. It's not hard to calculate because you just know the differential equation. It's really easy. Okay. You got a resistor. Well, now that spring dissipates some heat. You got some air resistance. It's not going to oscillate by itself forever, but it might keep going for quite a while if you got a good quality spring. We've got springs in here that can go for one. But you got to keep driving it. And you set up a circuit that drives this thing and keep adding energy at the right frequency. It's a natural frequency in the circuit. Okay. So let's just look at as much of the circuit. So we got conductor L. We got a capacitor with capacitance C. And we got a resistor with resistance R. We got some current. Well, if the current is I, then the voltage drop across the inductor got LDI dt, right? And if the current, if the IDT, okay, if I was trying to increase, then you have a voltage pushing this way, right? Voltage pushing this way is like it's positive here and negative here. So you do have a voltage drop. Okay. Now, if the capacitor is positively charged, you'll have, again, the voltage drop across the capacitor. If this is positive, this is negative. Okay. Positive, negative is a voltage drop. And if the current is flowing in this direction, then you have voltage drop across the resistor. And you can't have actual voltage drops across all three. Not possible because of conservation of energy. Voltage is your work per unit of charge. Okay, your energy per unit of charge, and you have a derivative. Okay. So might be that you have a voltage drop as you go across the resistor in this direction. But that your capacitor is positively charged here and negatively charged here, so your voltage increases as you go across the capacitor. Then it has to decrease as you go across the resistor. Okay, if the current is decreasing, then you have the voltage increase across here. So you have to have a voltage drop across the capacitor. Well, not necessarily. You can have either across the capacitor. You're going to have a drop across the resistor as long as the current's in this direction. If it goes in this direction, rising, falling, dropping, you got all kinds of combinations of what can happen. Anyhow, voltage drops in the counterclockwise direction. LD and IDT. Got Q over capacity. Okay. Am I doing that right? Intuitively. You've got more capacitance, you got the large voltage drop. That's probably not right. You can get confused on this, and you know, just apparently confused here. Capacitance is Q over V, so voltage is Q over C, right? It's the intuitive idea of capacitance is in charge per unit of potential difference, so the Q over C is correct. And then you got plus IR. Well, that has to be considered, doesn't it? Now, how many things in here? How many variables do you have? Is L variable? Is C variable? Well, it could be. You can have variable capacity, but we're assuming it's constant. And you can have variable resistor, but we're assuming it's constant. But I is equal. Better if you have the IDT and Q keeps changing, right? So they're two variables. You don't have to solve this equation with two variables. Well, pretty easy to fix that. Your current's just the rate at which charge is being deposited on the capacitor or moved off the capacitor. Okay. In other words, I is just CQDT. It's the rate of whatever the current is, it's changing the charge on the capacitor, right? And the rate of change is just the current. So I is dQ dt. And that tells us that we've got L times the second derivative by respect to T plus IR, well, that's the R first. R dQ dt plus Q over C equals 0. Well, and your book uses a lowercase I. I've been in the habit of using a lowercase I for a long time. That's because we had to chisel our math into the cave walls. I's formed from a lot of nice straight lines, and dots are hard to make because sometimes the cave wall chips off in an inconvenient way, so we use capitalized. Okay. And I can't get out of the habit. I always get that one thing. Okay. Anyhow, here we have this, okay? And if you write it in the book's notation, I could write this a little more compactly as L times. I'll go ahead and use a small I. It'll kind of switch gears on you here. Hopefully that's, it's not. I is DQ DT. When I wrote my numerator here, I have that I in my I. Okay. That is what DQ, isn't it? And then the I and Q, so the derivative of the Q. I keep this in terms of Q. Now, what are you gonna do with differential equations? You let Q equal some constant times e to the RT, right? And you get your characteristic equation. You just do a simple quadratic formula, or factor or whatever, and you get your R, and now you know for your charges, okay? And a function of time, very simple. So we're gonna do it, even though it's not, I'm not gonna test it whether you can do it or not. You know enough that we just dispose of that part in just a couple minutes, okay? And, you know, kind of review something that's one of the easier things in differential equations. Now, interpreting three different cases, you have a repeated solution for R. Okay, you have a complex solution or an imaginary solution, or just pure real solution. And that becomes important depending on the relative size of the R, L, and C. You have any of those. Okay. So if you have just a pure negative values of R, you have an exponentially decreasing. The positive values of R, you have exponentially increasing. Right. Charge. Okay. If you have pure complex, then you just have a pure e to the I theta. Cosine theta plus I sine theta, but you know, it's e to cosine of omega t plus I sine of omega t, and there's your oscillation, right? Okay. And if it's complex, then you're going to have a real part, which is an exponential, like e to the negative 0.02t times your oscillator, cosine of omega t plus I sine of omega t. And then times some constant, which is your amplitude, and that's it. Now, hopefully remember most of that, but we'll write a lot of that. Okay. So here we have the equation. So I'm going to go ahead and write out the solution, except first thing I'm going to do, I'm going to divide by the leading term because he would have wanted all of them. Okay, well, this implies if Q equals AE to the RT, the solution of this equation is just going to be now you pretty much use R in differential equations. Since I don't want to confuse lowercase r with uppercase r, although I don't think that would be a problem for you. I better change this to lambda. Now you get to think about eigenvalues and stuff. Okay, but you're used to lambdas. Yeah, doing that last year. Okay. Got this. So lambda equals negative r over L plus or minus square root of r squared over L squared minus 4 over r, so all that divided by 2. And we can immediately see that if RC is small enough, for example, we're going to have a negative under the radical, so we're going to end up with some kind of an oscillatory solution. And we're going to have e to the something times I. Okay. Or if L is large enough, okay, and a real high inductance, then this is going to be small compared to this. And that's again going to give us an oscillatory. Now there are a lot of other possibilities, but just take that and just for 3 or 4 minutes, do a little algebra with it and try to put it in a form that's simpler to look at. Just want to see what you do with that. And I just want you to get the idea that, yeah, we want to put that in a form that makes it as accessible as possible. We can already see stuff. We can already see that if you got some combination of large L and small RC, you're going to get oscillation. Okay. What are other possibilities? Well, if you don't have a capacitor, then you're kind of in trouble because you've got some kind of infinite here, right? Don't have a resistor. Well, you simplify the thing to the right extent, and those things don't become a big problem. Okay. So how else could you write this? Make it easier to manipulate. And I got to say something really ignorant. And did something really ignorant. When I said that I have capacitors, well, we're divided by L, not R. Okay. We get LC here. That should be an LC. And this should be an LC. Now, if you don't have a resistor, for example, still okay. So, you know, it didn't interpret. So, what's more? What can you do with it? One, to get the time constant there. I don't want R squared to the constant. That's what I want. We're not going to go too far on this together. Yeah, something's a little screwed here. We're going to stop at this point. So they don't really do the solution in the book. So we're going to play around with it, make sure I've done something boneheaded, left something out, but can't see what it could be. if you leave the resistor out, it can work. Okay. Two here takes care of the four there, and you end up with 1 over LC. So you end up with a square root of 1 over LC. And that gives you your imaginary part, and that's all you have. If, okay. As remembering something wrong, but it comes out of the equations. Okay, I'm not sure how long that recording went on, but it's what we got here. I don't like that R squared C that, but let's just say we don't have any resistance. Okay, we don't have any resistance, then the whole question, and then that's, you know, we take the resistor up, we get that oscillating circuit. Okay, and what's the frequency of oscillation? Well, if R is 0, this term and this term go away, and we just get plus or minus a square root of 4 over LC, that negative square root of 4 over LC, all that divided by 2. Well, if we factor out the 4, we get a 2, we divide it 2, we get the square root of 1 over LC, right? So I'm going to put a couple of question marks here. I don't really want to anyway. So if R equals 0, of course, if R equals 0, we can just leave this out of the equation. And we can immediately see that we get an oscillating circuit because we know. Go back to what we did with simple harmonic motion. Okay. We got m dx squared dt squared m times x double prime plus a constant equals 0, right? Which gave us x double prime equals like k over m times x, okay? Negative k over m times x. And we asked the question very early in the semester, okay, what functions have derivatives that are negative constant multiples of themselves? And that's sines and cosines. So we don't need to do anything fancy to understand that if this isn't here, we're going to get second derivative of q is negative q over LC. Yeah. Okay. So q double prime is negative q over LC. And the solution would be, for example, the cosine of 1 over the square root of LC times t. Now it's very easy to see that, okay? If you see what we talked about back in September about simple harmonic motion, which y'all did real well with on the final, they still didn't really totally grasp those connections, okay? So you might want to think through. It's a good time to think through them now. They can be okay. If R equals 0, then we can use this solution. We get lambda equals this. This term goes away, this term goes away, back out before, and it's okay. They call that omega. What do we call that omega? Our solution come back to be e to the lambda t. Well, A is going to become R Q naught. Be lambda I. Another reason I don't like using the little I when I do these is we usually use I for the imaginary. Now, in your engineering, a lot of times engineers will use J to avoid that. You've seen that, haven't you? I mean, you have seen this class. Yeah. I think you've seen it. Okay, so it's E to the plus or minus omega I. And that implies in a way you really don't have to do for this course, but you really just want to do it for your general perspective as you go into your upper division engineering course, okay? And that's what the thing there. And we did that a bunch of times. First semester, we were talking about oscillator. I mean, you get, you know, from this officially, you get a cosine of omega t plus I sine of omega t, or minus I sine of omega t. Arbitrary linear combination of those can then be any combination of cosine and sine, and you can use double angle formulas or various things to just bring that back in. There's some two angle formula. Bring that into the one cosine of omega t plus 5, and there you have an oscillating circuit. Okay. If you've got resistance in it, then you have an attenuation. You have a factor out here, and you're going to get something like a 1 minus 1 over the square root of LC, but somehow they're working out. But I haven't really figured it out. This is what I really want to see right now. Okay. And then see that, okay, if you have a small resistance, then that can have an effect. I don't like the R squared. It's irritating me. Okay. I don't know. That's not really how we're going to rearrange it anyway. But that's kind of the direction you always go in. Okay. And there's no problem. Okay. That's pretty much what I want you to see about alternating circuits, but we want to talk about phasors and stuff like that also, because it's conceptually kind of challenging. And I'm not going to go too deep into it, but you really need to see it. And then we're going to wrap that, especially about electrical, and what's the temperature. At your leisure, preferably before your subscription runs out. If you have time. I don't think you'll have a lot of trouble simply like that kind of stuff. Okay. Okay, well, anyway, you see why omega from LC circuit, an LC circuit is 1 over the square root of LC. Okay. It comes directly out of the differential equation. There's still something about this that makes me uncomfortable. Okay. But there's nothing wrong with that solution. Let's go to the solid. Let's see if we can figure out the inductance solenoid, the L that we multiply by di dt. Yeah, the backing of that. Okay. So we do, and we've done this before. We got some length here. We call this distance delta x. Now it's understood that we have a rectangular path through the interior of the solenoid here. And that these sides then are long, so we have very little magnetic field out here. And by the symmetry, as long as we're not too close to one end or another, whatever component of the field goes in this direction is going to be the same as the field would we go in this direction, since they're going in opposite directions. The contribution to these two sides to the line integral magnetic field is going to be zero. Okay, so that the integral around the path. Okay, so this is going to be a curve. Their path. Not all that curved except right angles and stuff. Okay, so see the path. See. We know that the integral around the path C of V, I'll say V dot D house. Okay. Is a multiple of, not gonna work too much about the multiple yet. The multiple of the enclosed current. Okay. So if you got current I, how much current have you enclosed? Okay. This equals the appropriate multiple of delta X times N over L times I. Okay. This is how many turns you have per unit of length. This is the length. Length times turns per unit of length, right? Okay. And then we have our constant out here that involves K prime. And fuzzy headed that I am, I think it's a 4 pi K prime or a mu naught. And let me just double check that to make sure I've got the right constant. Okay, I wanted to be sure it is what I said, it's 4 pi K prime or mu naught. Okay, so there's the integral of the magnetic field around this entire path. But that's equal to the magnetic field times delta X. Because by the symmetry, everything we have the equal magnetic field inside, or at least we assume that and the limit is the number of photons goes to infinity and so forth. If that's the case, and it's very close to being the case for the real inductor. So we have this, so of this in the field of the solenoid, which you could also write as U naught I times N over L, which I think in the notation of your text, which is a standard notation, I don't really quarrel with it. Yeah, it would be silly. And be like before we were trying to fight Mike Tyson or something like that. It's mu naught I times something I think it symbolizes M. You can look at that for me. Okay, that one. Again. And you probably do it in I, so that looks like the word M. Okay. This is what it is. And the book uses some symbol from N over L might be. Okay, well, anyhow, you got the magnetic field, right? Okay, so now what's the inductance? Well, if current is changing. Here, if current is changing. I'll use the okay. You get this. Now, if I happens to be constant. And. Okay, I've got an arrow over my B here. By the right hand rule. That's the X direction. There will be times the I vector. I'm going to take the arrow off of it. You know, it's either positive or negative. It's not going to matter for this derivation. Okay, so you have this. If I happen to be constant, of course, you have no change in the magnetic field. And remember, the change in the magnetic field what induces an EMF, right? Now your EMF induced would be negative d phi v dt. And what's d phi v? Well, cross-sectional area of your solenoid. Which is negative cross-sectional area times U naught N over L di dt. And now I've got a really bad notational problem because I'm using capital L for the length of this thing, or what length of whatever section, right? The capital L's inductance. That choice of symbols. So I'm going to change my symbol to a lowercase script L, which I write beautifully. Okay. I've got to replace all these. It's something else. There should be one. There should be one. One. There. Here, but this Danny. Well, induced EMF is L times di dt, right? And we're just dealing with magnitudes. actually be like negative LDI dt. So L equals cross sectional area times mu naught, which would probably be out front, times N over L, whatever your book uses. That. And for an ideal solenoid, another approximations involved. Field isn't totally uniform over the interior, but it's close enough that we get a pretty good idea of what the inductance of that solenoid on. Okay. So we could think, well, if we wanted to make an inductor out of 100 yards of wire, okay, wrap that around some kind of a core, preferably an iron core. We want to get a lot of magnetic field in there, right? Although that might be impractical, it's going to be close to other things. And we replace our mu naught by mu naught times, well, the permittivity of whatever the material is, okay? So it might be as much as 80 times mu naught or something like that. Okay, what's really not that? Okay, that makes sense. So we could actually figure that out. At 100 yards of this stuff, we've got a core of diameter 2 centimeters. So circumference would be approximately 6 centimeters. So we got close to 60, over 60, over 16 turns, about 16 turns for every meter. You got 100 meters, you got 1,600 turns. Thing have to be long enough to accommodate 1,600 turns. You'd have to worry about the resistivity of the wire. You get a fair amount of resistance. You don't use fairly thick wire. If you use fairly thick wire, it's hard to get 1,600 turns around a small core. Okay. But yeah, you can play around with that. You just play around with the geometry of the thing. And analyze it yourself, because it may be mistake somewhere. If you understand Ampere's law about the integral of the V D S or whatever B dot D S, and of course, you know, in multivariable calculus, you deal with line integrals, you should understand that pretty well. And everything I explained about this, it's pretty easy to derive this. If you make the assumption that we got a QD of. Okay. Also, you want to look at the circular solenoid. Okay. Analyzed very similarly, but with a path that goes all the way around, because the symmetry allows you to do that. Okay, so make sure you think that through. And then, you know, do the homework. It'll run you through the whole thing.